Verilog provides support for gate-level modeling. This is achieved when using the built-in gate primitives in the Verilog language. For example, the following gate primitives are available in Verilog. If we take the AND gate, one way in which the gate can be used is to provide the gate name, which is AND, and then make connections directly to the gate. Using the built-in gate primitives, we make connections by just listing the connections in the order shown, with the first connection for the output and the remaining connections for the input. The second way in which we can use the gate primitive is as follows. Use the gate name and provide a name, in this example gate 1, followed by the connections. Out, in 1, in 2. And in Verilog we terminate the statement with a semicolon. So using this we terminate it with a semicolon also. A key point to note is that this first connection is for the output. A benefit of this approach is that we can make a small modification to our code to allow more than 2 inputs. So for example, if we want a 3-input AND gate, our first connection is still the output, and now we can just list 1, 2, 3 connections which are all inputs. And in this example, for a 5-input AND gate, first connection is still the output and remaining connections are the inputs. There are no module declarations for these built-in gate primitives. They are defined in the language. When using gate primitives, we're operating at a low level of abstraction. So these gate primitives are not widely used in practice, but we will use these gates to model some simple designs. Going forward, our goal is to move up to higher levels of abstraction when modeling designs. Let's put some of our recent Verilog concepts together with an example. And the example we're going to use here is a 4-bit comparator, whereby we've 2 4-bit inputs, A and B, and a single bit output indicating whether A is greater than B. It's always important to try some sample values to help understand the problem at hand. In our example, let's take the 4-bit value 0, 1, 1, 0 for A. This binary value is equivalent to 6 in decimal. And for B, let's take a value 1, 0, 1, 0. And this is equivalent to the value 10 in decimal. And the purpose of our comparator is to check to see if A is greater than B. Well, is 6 greater than 10? It's not, so the output is 0. I've just included the decimal value so that we can quickly perform the comparison. However, our 4-bit comparator operates on binary values. Let's take another example. Let's take 0, 1, 0, 1, which is the decimal value 5, and the value 0, 0, 1, 1, which is the decimal value 3. So in this case, A is greater than B, and the output will be 1. To begin, we'll start with comparing one bit to another bit, so just a single bit comparison. And we check here to see if A is greater than B. So in our example, A and B are just single bit values. For example, 1 and 0. So here A is 1, B is 0. Is A greater than B? Yes, so the answer here is 1. And if we look at all possibilities, we can complete a truth table. When we compare A with B, is A greater than B? In this case, is 0 greater than 0? No, so our output is 0. Is 0 greater than 1? No. Is 1 greater than 0? Yes, our output is 1. And is 1 greater than 1? No, our output is 0. So the truth table captures a single bit comparison. As we saw previously, it's possible to construct our truth table in the manner shown here, a more compact form, but represents the same information. If we were to use some simple gates to implement this truth table, it would look like this. The output is only true when A is 1 and B is 0. That's this case here. And we can implement that as shown, invert B and AND the result with A to give us our output. Now that we know how to compare a single bit with another single bit, Can we use this to help us build an n-bit comparator, or in our case our 4-bit comparator? And the answer is yes, but we need to make a slight modification to our single-bit comparator. Our single-bit comparator just takes a single bit A and compares it with a single bit B. What we want to do is to compare a 4-bit number with another 4-bit number. Our 4-bit numbers are denoted using capital A and capital B. It turns out that if we take the 3 lower bits of A and the 3 lower bits of B and compare them, we can use that result with the 2 most significant bits, lowercase a and lowercase b, and generate a final result. So what we can do is our 3-bit comparison can generate a value which we denote g in, and we can feed that into an operation using lowercase a and lowercase b to produce an output g out. And this is what we want to look at here, creating a bit comparator that compares 2 bits but uses the result from comparing other bits within the number. The best way to understand this is with an example. Let's say capital A looks like this and capital B looks like this. What we're saying here is that if we take the lower 3 bits of A and the lower 3 bits of B and compare them, performing this comparison on these 3 bits give us a result 0. In other words, this 3-bit value 0, 1, 0 is not greater than this 3-bit value 1, 1, 1. So our Gn is 0, and if we feed that information into our modified bit comparator, we now have small a with the value 1, small b with the value 0, and we can use this value then to determine what's the output for the 4-bit comparison. In this example, just taking the lowercase a bit and the lowercase b bit and the g in bit, those 3 bits can be used to obtain the g out value. And that means what we need to do now is to create a truth table with 3 inputs, a, b, and g in, and 1 output, g out. Let's do that then. To complete our truth table, we have our 3 inputs, a, b, and g in. The first case we look at is the case of small a having a value 1 and small b having a value 0, which is this entry here for AB. And what we note is that it does not matter what the value of Gn is, in that this 4-bit value will always be greater than this 4-bit value when you have a 1 here and a 0 here. So it does not depend on Gn, and the output will be a 1. If we take the case of 0, 1 for the lowercase a and lowercase b, we're now considering this case, and in this case the result of the comparison again does not depend on Gn, because anytime you've got a 0 for small a and a 1 for small b, the result of the 4-bit comparison only depends on these 2 bits, and the output will always be 0. Let's now take the case of small a being 0 and small b being 0. In this situation, the 4-bit comparison only depends on Gn. When you compare this 3-bit value for a with this 3-bit value for b, the result, which is Gn, determines what the output of the 4-bit comparison is, because the 0 and 0 here will not alter the result from the 3-bit comparison. So that's this situation here for AB00, 0, and the output is just Gn. So on the first row here, Gn is 0, and on the second row, Gn is 1. And we have a similar scenario when we take the case of AB equal to 1, 1, and that's this column. So in this situation, Gn determines what the output of the 4-bit comparison is. And remember, Gn is the result of comparing the lower 3 bits of capital A with the lower 3 bits of capital B. And that produces 0, 1. So we can summarize this as follows. If small a is greater than small b, so in other words, if you have a 1 here and a 0 here. In that case, G out is equal to 1. It does not depend on G in. And that gives us these two 1s here. The other scenario in which we get a G out of 1 is the case of the A bit being the same as the B bit. So for example, if you've got a 0 here and a 0 here, so if those two bits are the same and Gn is equal to 1, then the output G out is equal to 1. So that would give us this output here. And if you have a 1 here and here, so again A is equal to B and Gn is equal to 1, then G out is equal to 1. So that occurs for this entry. So these are the only 4 entries in our truth table where the output G out is equal to 1. So to summarize, what we've done here is we've modified our single bit comparator to take a third input, which is then used to produce our single bit output. And this third input, Gn, is the result of comparing the lower 3 bits of capital A with the lower 3 bits of capital B.